We are live now.
Vinu has not joined anyway, so I think he will join.
So we are live
Is
now.
it
You can share.
live? Okay.
Yeah. Please go ahead.
So welcome all of you. Welcome Professor Ravi. Welcome Dr. Krishnan, Professor Aditi Sen Day for this. We are organizing this 40th Professor Ananthakrishnan Colloquium under as a part of Azadi Ka Amrit Mahotsav as well. And the topic is quantum technology. But before start, I will just briefly read out Professor Aditi Sen's uh, background. So Professor Aditi Sen De from Harish-Chandra Research Institute, Prayagraj, earlier called Allahabad. She is a Professor H, and she, along with Professor Ujjal Sen and Professor Arun Kumar Pati, established a quantum information and computation group in 2009, and they have 15 PhD students presently in the group and 5 postdocs working in the field of quantum information and computation. And Professor Sen did her doctoral work in University of Gdańsk under Professor Marek Zukowski, and then she was Alexander Humboldt Fellow, and she worked with Professor Levenstein in Hanover, and subsequently she was Raman Y. Kayal Fellow in ICFO, which is known as the Institute of Photonic Science in Barcelona, and subsequently she was also an assistant professor at Jawaharlal Nehru University. As a recognition to her phenomenal contribution in the field of quantum computations, she was awarded prestigious Shanti Swarup Bhatnagar Award for the year 2018. So we welcome Madam for this 40th Professor Ananthakrishnan Colloquium. Please.
Thank you very much for the invitation and giving me this opportunity to present the area in which I'm working. I hope that this is a virtual meeting, but at some point I will be able to visit. I was actually looking some of your works, although I know a little bit of, very little on this area. So I will be interested to know. So can I share the screen now?
Please.
Please stop me if you cannot hear, because my internet is a bit bad shape today. So can you see my screen and the voice is clear?
Yes, it is clear, Madam.
Hi.
Yes, please.
Okay, so I will be talking to technologies. So I will be talking about technology that we are planning based on quantum physics. So in our daily life we use several technologies. Today I'm talking about two things. One, another communication devices. We are kind of in our daily life, these two are the integral part of our daily life, our uses, etc. So the communication devices can be classified categories. Communication without security is that when we want to send some information, the information is not known to anyone. On the other hand, there can be a communication is actually so in that, typically sender shows the information in such a way that receiver only gets the information. No third party can acquire this information. And this is called secure communication. I will explain in detail what is cryptography and what is secure communication. So our aim is to build technologies based on quantum physics. So I should say these are called quantum technologies. So computer and rather the quantum computer or usefulness or what is the reason that you want to build. So the computer that we are using nowadays, so the laptop where I am giving this presentation that we are using, all I call classic computer because they are built on the principles of electronics. Now, this is probably a much more powerful computer hub where all the computers are connected. So these stations we can perform much more efficient training things. So the usefulness of classical computers in this audience doesn't require to emphasize this usefulness. Because the classical computers can be used range from educational to banking, etc. Use computers to write documents, to indicate and so on. At the same time, this classical computer can be used to do mathematical calculations. That also all the academic people know very well. That to do certain mathematical calculations, we use classical computers. So the basic of a classical computer is it, which is one of the 0.1. So if you have input, then in a classical computer, input is translated in 0 and 1. There are logical that match input, and finally gives us output, which is also a string. It these are the three processes of three steps typically a computer follows. We give the input, there are logical, we manipulate the input, then finally we get the output. Now I will talk about the problem, a mathematical problem. In particular, I am interested in a problem where for a given number, we want to verify whether this problem. Now, this is possible because even in schools we learn that, say, till 100, in a primary school, children usually learn what are the prime numbers. But I am talking about prime numbers of arbitrary digit. So if you this 10-digit number, now this digit I have a time keep in mind is odd. Then we have to solve whether this number is and not. And to write down the program in a computer, okay, now it's easy. Actually, this number can be verified. This number is it's right. A program which actually tell me the answer for an arbitrary number. So that can be digit number or something. So this problem is simple because until 2002, where there's 3 people from IIT actually solved this problem. So they proposed an F algorithm by which they verify whether the number is prime or composite. The important point is that they can verify or their proposed polynomial time to solve this problem. Now, this polynomial time is important. So one can think that it's a complexity class. So that means it's in a reasonable time. So this is the polynomial as we learn. If you want to solve a digit number, then take
Padmagar, is it connection lost or something?
Sir, I think that connection has been lost.
Okay.
Hello, can you hear me, ma'am? Hello, ma'am, your microphone is. Ma'am, your microphone is mute. Can you please unmute?
Please unmute, Professor Sen, your mic. You need to
I'm
unmute
sorry.
your mic.
I have unmute. Can you?
Yeah, but
Hello?
yeah, audio was not coming very clearly. Now let us see. Yeah.
Okay. So can you see my screen and can you hear me?
Yeah, but the
Hello?
yeah, now the presentation has come.
Yeah. Okay. So I want to put the prime factors of an integer. For example, if I give you 45, you know the prime factors as are 5 and 2 3s. Similarly, you can find prime factors of 72. You can also find prime factors of, say, for example, 8-digit number and so on. Now the question is again that if one gives you a 1-digit number, then if you use 1600 workstations, then even you use the powerful computers or the connected powerful computers like 1600, then the current algorithm takes around 8 months to solve this problem. And if you just take in 120-digit number to 250-digit, then it takes almost the year of the universe. So, in other words, to factor an arbitrary n-bit number, currently available algorithm in our classical computer takes exponentially n steps. To be very precise, it takes these many steps. So this is actually bad news because we cannot solve this problem. So there is no efficient classical algorithm exist yet which can find out prime factors of a given integer of an arbitrary digit number. But in 1994, it was shown that quantum mechanics can solve this problem efficiently. And this is known as Shor's algorithm, or is found by Peter Shor, where he's shown that quantum mechanically it can take polynomial time. So this is the exactly time, the logarithmic of. So if I want to solve an n-digit number, it takes this many steps. On the other hand, if we use our classical computer, so the known algorithm takes this many steps. That is the sub-exponential steps. So this is Peter Shor, and so this is a very, very good news because quantum mechanics promises efficiency. And this is the first one of the to build quantum computer. There are several algorithms proposed over the time, like Grover, Deutsch-Jotza, etc., where quantum mechanics promises to reduce steps compared to their classical counterparts. So these all algorithms can solve certain tasks by using quantum mechanics in less numbers of steps compared to the known classical algorithm. So these are the problems that that actually gave us motivation to build a computer based on quantum physics. Now, quantum mechanics or quantum physics describes the properties of microscopic particles which are in atomic, subatomic level. As we know, it was formulated around 1920s by several great scientists. to this Einstein, Schrödinger, Heisenberg, Dirac, Bose, and these details are important because this actually include all the experimentalists to to develop the modern quantum mechanics at our colleges. This is probably the famous picture people have seen. So this is a survey of 1927, the quantum mechanical in most of the great scientists who helped to build the quantum mechanics of our present. In here, to describe situations in a physical systems, we require vectors in a linear space with an angle defined. And the linear space in which angle is defined is called the Hilbert space. And we are interested in a two-dimensional complex Hilbert space. So that two-dimensional complex Hilbert space can represent the spin of an electron. And that gives us a basic unit of a quantum computer. As I have discussed, in classical computer, the basic unit is bit, so it is one of the zeros and one. On the other hand, in quantum computer, the basic unit will be quantum bit. In short, it is a qubit. And mathematically, or this is an arbitrary two-dimensional quantum state, so which can be represented by the block sphere. And if I choose spin degrees of freedom, this is an arbitrary two-dimensional quantum state. So alpha up plus beta down, where alpha beta are complex numbers, and there is a normalization constant condition which I haven't mentioned here. So this actually tells that in quantum mechanics, one of the is a superposition, which means that there is a cat which can be alive at the same time there can can be dead. So we can have a state which is a superposed of alive and dead cat, and this was probably mentioned, and this is no Schrödinger cat state. So existence of this kind of states ensure or give us the power to get the better efficient computer. The success of Shor's algorithm. So Shor's algorithm starts with the state initially, and this finally gives a power to solve the problem, that is to factor integer into its prime factor in an efficient way. There is a time in polynomial. Now, in classical computer, we give some, then the evaluation get, I call classical get. We know that we are AND or not get or NAND get. And in quantum computer, gates require the quantum state. The two important gates are Hadamard gate and CNOT gate. So Hadamard gate, as you see, that it takes some quantum state for superposed state. So this is the important gate for getting better efficiency. And CNOT, although you cannot see because it just whenever the first qubit is 1, then it flipped, but it also can create a very important states, which I will discuss later, which is known as entangled state. So this quantum computer is no more theoretical prediction, but it's there are a lot of experimental achievements, and there is a by using ion trap quantum computer, they have recently created an 11 qubit quantum computer where they demonstrate or they verify this two quantum gate that I mentioned. But this is a small scale quantum computer. I think this one is a very well known and very publicized work where Google declared 53 qubit quantum computer, and they claim that they have obtained some quantum supremacy. Although there are a lot of debate going on from IBA and the Chinese group where they are able to show that this is not really supremacy, but of course it shows that quantum mechanics gives us certain advantage which you cannot get in a classical computer. I also work in this direction. I'm not going to that. We are looking for a physical where that physical substrate can be used to build a quantum computer. Now, this is the technology timeline which European Union has published, where they say that they are planning or they're heading towards quantum computer 2030, where from the academicians, there are several computer companies like Google, IBM, Intel, many startups companies are trying to build computer or quantum circuit. There are already small-scale quantum computers that have already been built by IBM and Google and many other companies, but that's up 100 qubit. Although to really show the advantage that I have described, like Shor's algorithm, where we can outperform or we can show that the quantum computer is better than the classical one, we require to build a computer which is around 1,000 or more than 1,000 qubits. So that we are still far away from that, but there are hope that one can build that. Here, I just want to emphasize that this is really a revolution in technology, because like a better lantern and candle cannot lead to a LED light or electric bulb. Similarly, making a better classical computer doesn't lead to a quantum computer. One has to build from the scratch. One has to build. These two are based on two different principles. One is based on classical economics, classical information theory. On the other hand, quantum computer is built by using quantum physics or quantum mechanics. Hello, can you hear me properly?
Yeah, we are able to hear. Sometimes
Yes.
voice is breaking, but now.
Yeah, yes, we are able to hear.
Okay.
Yeah.
Okay. Can you see the screen? Yes.
Yeah, we can see. No problem. Yeah, there is a small gap.
Thank you.
Yeah, only some breaks are happening in between discontinuity.
Okay. Okay. I'm sorry, but.
Yeah, no problem.
Yeah, so now I move to the second part of my talk, where I will talk about communication devices. So in this COVID scenario, probably there is no point to emphasize the importance of communication devices. So I think this is another revolution we see in communication devices. Probably I am from this era where I used to write letter to send information of our family to my relatives whenever we used to send letter via post. Now probably we send email. So this is also a revolution. This can be called the first kind of technological revolution, and we are talking about second generation revolution in technology. So the communication that I am talking about involve at least two parties, which we call Alice and Bob. They are situated in two distant locations, say Kolkata and Allahabad. And Alice wants to send some information to Bob. So this can be two celebrities or can be normal people. Now, Alice's aim is to send some information to Bob. This information, now we understand, can be classical or can be quantum. Classical information means Alice will send some bits to Bob, or Alice wants to send some quantum state like a qubit that I have described, that is an arbitrary two-dimensional quantum state to Bob. Now, it was shown that if we
Padmakar, is it lost connection?
Yes, sir.
So she has to connect again. You have to unmute, madam.
So now can you hear me and can see the screen?
Yeah.
Hello? Yeah.
Yes.
So I will be talking about classical information transmission via quantum states. And this is known as quantum dense coding. Now, why it is called dense coding will be clear in a minute. So suppose I am interested in a classical in particular. Suppose Alice is situated in Kolkata and Bob is in and Alice wants to send a weather report to Bob. So there are 4 possibilities that Alice wants to send, whether it will be sunny today or windy or raining or snowing. Okay, snowing is not possible, but let's assume that this is also a possibility. So there are 4 possibilities. And that means there are 2 bits of classical information that Alice wants to send to Bob. Now, they are pre-decided before starting the protocol that Alice will send a blue ball to Bob if it is sunny. If it is windy, then gray, raining blue, green, and snowing yellow ball. So this is pre-decided before they start the protocol. Now, in the morning, Alice wakes up and finds out that today it is sunny. Then Alice will send blue ball to Bob, and other balls snowing, windy, or Alice buys this ball, or Alice has this ball. Then Alice put it in a box and send it via courier, say, to Bob, who is Pune. Now you see that the Bob can distinguish these balls from the colors of the ball. And so Bob can understand from the color that whether it is sunny or snowing or windy or raining. So Bob can decode the message. And you see here there is a process called encoding, which where Alice uses these 4 colors of the ball. Then Alice sends via some medium, and then finally Bob decodes the message. So there are 3 steps. So you see that to send these 2 bits of classical information, Alice requires 4 distinguishable objects, that means 4 dimensions of the system. Now the question that we are asking, can quantum mechanics give us any advantage? And indeed it is, because suppose Alice and Bob share this composite system, which we learn to be a singlet state. Here zeros can be an up spin of a spin-half particle, and 1 can be a down spin of a spin-half particle. Then, depending on the message that Alice wants to send, Alice performs an operation, quantum mechanically allowed operation, actually unitary operation, these 4 unitary operations on her part of the protocol. And one can check that by performing these operations, Alice can create orthogonal state, orthogonal shared state between Alice and Bob. So after performing this unitary operation, Alice sends a particle to Bob. Now Bob has both the particle, and both the particle are either in the state psi minus singlet state or one of the triplet state. Now, as you see that these states are orthogonal, so they can be distinguished just like a color of the ball. Here I have to perform a quantum mechanically allowed measurement to distinguish them. And if Bob gets psi minus, that Bob is sure that in Kolkata it is sunny. If he gets phi plus, then he is sure that Alice is today it is raining in Kolkata. So this is the decoding part of the process. So Bob can decode the message, but interestingly here you see that to send these 2 bits of classical information, Alice requires to perform operations which is only of dimension 2, because Alice's part of a singlet state has dimension 2. So we see that we can double the capacity by using quantum mechanical So, model of the following, that in a classical protocol, to send 2 bits of classical information, Alice require 4 dimension. On the other hand, quantum mechanically, Alice require 2 dimension, provided Alice and Bob share a priori an entangled state. Now, I haven't defined what is entanglement. Before I give the definition here, just again tell you, emphasize this thing, that this dense coding protocol also has been realized experimentally by using degrees of freedom of photon in Vienna by Anton Zeilinger group. So this is in 1996, and now there are much more advanced protocol they are doing. So the key ingredient for the success of this whole story is the property of a quantum mechanically shared state, and the property is known as entanglement. I briefly define what is entanglement. So if Alice and Bob situated in 2 distant locations, then Alice creates a quantum mechanical state, Bob creates a quantum mechanical state, then the joint state looks like that. So suppose I have a photon, I'm doing experiment with photon, then Alice prepares in her lab certain state, Bob prepares in his lab certain state, then the joint state looks like this. And these states are called the useless or unentangled state. So these states can be prepared by Alice and Bob even when they are situated in 2 distant locations. Why they are called useless? Because these states cannot be used to perform or to get the capacity that I have shown for dense coding protocol or other protocols. The example that I have said, that it's up spin in Alice's lab, up spin in Bob's lab, or down spin in Bob's lab. So this will be the joint state. On the other hand, we are used to get the dense coding protocol successful. Alice and Bob has to create an entangled states, and these entangled states, those states which Alice and Bob will not be able to create when they are far apart location. Then the next obvious question is, how will they share? Okay, they share in this way. There is a source. Suppose the source is in Delhi. So source produces this entangled state and sends one particle to Kolkata, another particle to Pune, so that Allahabad and Pune, the Alice and Bob pair share an entangled state. This can be a possible way to create an entangled state. So there is a mathematically this state cannot be in this way. And singlet state is an example, or triplet state is an good example in entangled state. So you can think the source is a provider, who actually we buy entangled state from them. So whenever I require, they will send one particle to Kolkata, another particle to Pune, before we start performing. So one thing in this also.
Padmagar, it's lost again, or?
Hello?
Yes.
Hello, can you hear me?
Yes, yes.
Yeah. Okay, so there are, although there are, the detection procedure is difficult, but there are a lot of experimental achievements in this direction. So as I said already, the photon is probably the good physical system where it has been realized. So this is a famous experiment in 2017 by Chinese group led by Professor Pan, where they use satellites to create an entangled state. And then from satellite, they send one particle to a city, another particle to another city, where these two cities are around 1200 kilometers apart. So in this way, they create an entangled state and they perform certain tasks. So which actually tells us that it is possible to create an entangled state between Kolkata and Guwahati. Probably a bit difficult to create an entangled state between Kolkata and Pune because it's more than 1,000 kilometers. There are other physical systems like ion traps, as I have mentioned. They can create entangled state, highly entangled state between several qubits, which are important. Also, by superconducting qubit, they can create entangled state between 20 qubits. So now the main goal is to create not one-to-one communication, because that has a very limited commercial use. So now people are trying to build quantum communication networks where entanglement or the communication protocol can be performed, where this is between large distance, several people will be connected. So in this direction, a lot of work are going on. For example, recently we have published, it's in December 2020, we actually find out a method how to share quantum resources in pre-decided node in a network. So, and how to really identify whether a state is entangled or not. As I said, that this detection is not easy. And we have done a lot of work in recent years on this direction of quantum communication network. I think I have some few more minutes, so I just end up with the last part where I will talk about secure communication or cryptography. So up to now, all the communication protocol that I have discussed is based on where there is no security issue. So for example, if I want to send, if I am a reporter of a newspaper, and I want to send certain information to the editor, there is nothing secure thing there. So I can send these informations via public channel. On the other hand, there are several issues, several tasks where the security is the main issue. So where Alice, for example, wants to send some classical information to Bob in such a way that third party, who is the eavesdropper, cannot gather any information that is sending to Bob. And we know this is extremely important in our daily life, from internet banking, where we only want to connect. So we want to give the login and password to the bank only. So we want to communicate between our information to the bank, not to anyone else, not the third party, when we do internet shopping. And also in the national security, this can be a very important issue. And probably, probably COVID-19 situations, we realize that internet banking or all the money transactions through internet is extremely important. And everyone, we get several messages, SMS, that we should not answer or we should not share our PIN or password with others. So this tells us this is extremely important. And probably this secure communication was used from ancient time and also importantly in World War II. So I'm not going in that story, but many of you know that there was a kind of disaster from German side because of this cryptographic failure. So all these classical cryptography systems that we are using nowadays are, the security of them are based on the fact or on the belief that some mathematical problems cannot be solved in our computer in polynomial time. For example, this mathematical problem can be a prime factorization problem. So the security is based on that fact that we cannot solve prime factorization problem that I have described in the beginning of my talk in polynomial time. So this actually tells us that all the banking or all these things that we are using will be insecure in when there will be a quantum computer. Because the mathematical problems we already discussed that can be solved by using quantum mechanics. So quantum mechanics makes all these crypto systems, or quantum computer very specifically, makes all the current crypto systems insecure. So what is the remedy? The remedy again came from quantum mechanics, because quantum cryptography, if we build quantum cryptography, then that security is based on the validity of quantum mechanics, and that remains secure even when there is a quantum computer. So this is very important, and it was the two important protocol is Bennett-Brassard 1984 and Eckert 1991 protocol, where to generate quantum key, instead of a classical bit, sender has to send sequence of randomly generated quantum state to a receiver. And very importantly, the quantum physics, the laws of quantum mechanics, the principles of quantum mechanics ensure that if eavesdropper, the third party, disturbs the system or wants to gather information, disturbs the quantum state that is flying from Alice to Bob, then Alice and Bob, the sender and the receiver, they can detect the eavesdropper, the third party. So this is a good news that presence of eavesdropper can be detected was actually shown initially by Utters and Zurek. And this is kind of known as a no disturbing theorem. So this is Bennett, Brassard, and Eckert who actually give the cryptography protocol. Again, probably the question comes that whether it is only a theory. It's not, because this is a very advanced subject, quantum cryptography. Already in 2001, there is an experiment where the quantum crypto system are built or shown or demonstrated in two points of a Geneva lake, Lausanne and Geneva. And later on, even in the realist in our cryptography system was introduced and the security was analyzed, but there are still several open questions, because the security is based on certain analysis of how powerful our eavesdropper or what are the tools eavesdropper use to gather information. So it depends on several things. And this was initially there is a football World Cup in South Africa where they use quantum crypto system. There is a Geneva elections where also they use quantum crypto. So this is the group of Nicolas Gison who has done this Geneva experiment. And in this respect, I just want to flash some of our recent work where we also prove some complementary relations which provides a bound on the secret key rate on a quantum key distribution protocol. Just recently, 2 weeks back, we actually use something nicely parity time symmetric evolution and show that can have some implications in quantum cryptography. There is something called monogamy of quantum correlation, that is monogamy of entanglement, which tells us that if Alice and Bob is highly entangled, then eavesdropper cannot be entangled with Alice and Bob. So this is a very important applications on quantum cryptography. Typically, in a real experiment, Alice and Bob cannot have maximal correlation, so it will be some noisy state. And then Eves will be weakly connected to Alice and Bob. And so there is a trade-off between the entanglement between Alice and Bob and Alice and Eve. And that have an impact on the secret key date or the success of the security of the of quantum cryptography protocol. And in our group, we extensively work on this. Even we write a chapter of the book. If you are interested, I can talk later. And recently, we also have proven some no-go theorem called no-masking theorem, where we show that can also have applications on quantum cryptography involving multiple I think my time is up. So, in last 5 minutes, I try to convince you that quantum mechanics can revolutionize our computation and communication capabilities, which is with and without security. So as I said that in 2018 already, or even before, quantum cryptography is already a reality. And we are heading towards quantum internet, which I give you a hint that we want to build quantum communication network. And probably final aim is to build a quantum computer. But here I should emphasize there are also several small scale quantum technologies people are trying to build. For example, quantum battery. There are applications in quantum metrology. There are also quantum sensors and so on. So these are also important. I have time. These areas if we want to is the current of my, they are also students that are presented is actually and who are with me now. Sharif is more in my but he's in a headed by my around 90 and
Your voice is breaking, actually. Is it the last slide you showed that?
yeah. Hello?
Yeah, hello.
Yes.
Are you able to hear us?
It was throughout the session.
Yeah, throughout
yeah,
there was.
I can hear properly.
Okay. In between, actually, the voice was getting stuck many times. It's not coming very clearly. It was breaking many times.
Yeah, sorry,
Could be
because
bandwidth
I
issue.
have an internet problem.
Oh, I see.
Yeah.
But anyway, it was very interesting, very new for us, and but maybe I'll just request if Professor Ravi is there and Dr. Krishnan, if they have any questions, or then I will find anyone in the YouTube audience has any questions. Professor Ravi, if you have any.
Can you hear me?
Yes, now
Yes,
we can.
Oh, okay, fine. So, I mean, it was a very interesting talk. I just have a very layman's question. how far are we from using it in various applications? Let's say I want to use it in climate modeling or somewhere. How far is quantum computing from using it in everyday, the kind of problems that we look at, massively parallel or highly computational kind of a thing?
Can you repeat?
Are you able to hear us?
Yes.
Could you hear Professor Ravi's question?
No, can you repeat? Sorry, I got disconnected.
So he has asked that how far we are from developing a quantum computer for real world, say climate related modeling problem issues. Yeah.
Yeah, I think it's, as I said, there is a small scale quantum computer available, but it's about 100 qubits. So that computer can solve certain problems which we can solve even in our normal classical computer, and even a more powerful computer is available which can do better than a 100 qubit quantum computer. It is true that there are some experimental results which shows quantum supremacy. That means they can solve certain problems, say, in one day, which by quantum computer they can solve it in few hours. So that actually gives a polynomial efficiency. But really, to get an exponential efficiency that I have shown you, we are far because we need around 1,000 qubit quantum computer, which is quite hard.
Yeah. Partha, I have one question.
Please.
Thank you, Professor Aditi. It was a very interesting talk. Most of us are, our thinking is all in the classical way, and I can say about myself. So I couldn't get much of this quantum idea of computing. But one question I have, you were telling about prime factorization, because we have done this to find whether it's a prime number or not. We have written Fortran programs to find it. And you said that if there is a so we can do it in the classical way. And you mentioned about a 129 digit number. If we were to find the factorization in the classical, it would take some, I don't know, how many, some thousands of days or something.
Yeah, no, the question is not that there are two problems that I have talked about. It's the problem state, which our fee nowadays give to our students about this. So I give you a number, you have to tell me whether the number is prime or not. This is solved, and this you can do it in a classical computer.
Yes.
I ask a different question. I give you an integer, okay? Say 100-digit integer, and I have to you have to tell me all the prime factors of that integer.
Okay. Yeah. See. Okay. I understand it. It is a time. It could be time consuming. But one solution is, can we not, if we make a table of all the prime numbers, can we not have it as some kind of a ready reckoner to go and quickly find it? I'm just thinking in a very conventional way. Would it not solve?
Yeah, but I think
so. All the
but the question is whether you have to write a program not only for a single integer but for any arbitrary integer.
Yeah.
And
true.
If I give you a 100-digit number, then whatever known algorithm is available. So there is a computer science, I think it's called computational class, complexity class. Yes. And you can show that in this computational complexity class, it actually takes a sub-exponential time.
Yeah. So the computational complexity is much lesser with the quantum computing. That's what you said, isn't it?
Exactly.
Yeah. And how does that happen? Because you showed the computational complexity with the classical computer.
Because this happens because as I just mentioned, because it's a very complicated algorithm. But I have just mentioned the initial state that one has to prepare. As you see, that will be a very highly superposed state. You can think that several cats with live and dead and so on make state, which actually classically is not available, because classically any state that are available are orthogonal, like distinguishable. I can distinguish, right? So whether it's a wavelength of wavelength of different wavelength of laser, I can distinguish by a wavelength.
Okay.
Quantumically, there are states which you cannot distinguish.
Yeah. So the algorithm
So if
itself
I
is different.
here
Isn't
in
it?
the
Sorry.
exactly, the starting point itself is different. Yes.
Okay. Yeah. Yeah. Thank you very much, Professor Aditi. Yeah.
No, thank you. I mean, thank you for the question. Actually, I am really sorry that the last day when I did checking that our internet was down. Today also our internet is down for some reason, and
Okay.
so I have to. I am using data to do that. So there are a lot of problems. I'm really sorry.
Okay. No problem. No problem. Thank you.
Just one last question, Professor Sen, that although, I mean, it is very new for me also, I mean, but I will start reading about this more as you have introduced today. So this, the fundamental is that your qubit, right? That is the fundamental of all this, where it is starting. And as you are telling that it reduces the dimension, right? You are giving that example of rain, snow, and so on and so forth, 4 dimensions. Then when the communication happened, the quantum communication makes it 2 dimensions. So is it the key that it reduces the dimension so the process becomes faster? And qubit is
space is bigger due to the superposition of quantum state. So in classical world, if you can see as a vector, then the vectors are only classically we have only orthogonal vectors.
Right.
Okay. Now I am saying that there are more vector in between, because non-orthogonal states also exist in quantum mechanics. So in some sense, the space is much bigger, and that gives you the power. So if you look at the sphere, okay, so in a sphere, only the poles are allowed in classical world, because poles are either 0 or 1. Whereas quantum mechanically, the qubit is the surface of the sphere. So all the points of the surface of the sphere are allowed. So you see that it gives you an infinite number of points. On the other hand, classically, you have just 2 points on the pole, which is 0 and 1. And that gives you the power.
Very interesting and emerging field. We are all looking forward that one day our classical computer, whatever deadlock, all will be broken by this new technologies. And there is no questions in the YouTube so far. So we thank you, Professor Sen, for sharing your time, accepting our request, and giving a very excellent, motivating talk. Thank you so much. Thank you, Professor Ravi. Thank you,
Thank you,
Jason.
Professor Aditi.
Thank you.
Thank you.
We can go offline. Thank you. Thank you, ma'am.